Hi guys, this is the video tutorial for the homework that I'm giving you this Monday. That would be page 49, numbers 10 through 26. Now you're going to notice that I've already listed some problems on the board, and these are problems from your homework, but what you might notice is that these are not the exact same problems that I've given you. However, they are exactly the same format. I'm asking you to do the same thing. So what I intend to do here is walk through these ones with you, and hopefully it'll give you a good grasp of what I'm asking on each section of the homework so that you can actually puzzle your way through the problems that I did assign you. Okay, and we can go through these in order. So actually I did want to start with number 10. Now like I said, this isn't number 10 from the book. However, this is exactly like what number 10 is going to ask you to do, which is, in this case, they give you two equal fractions. Now, we haven't said this in class yet, but we're going to refer to that later in the year as a proportion. Two equal ratios or fractions form a proportion. And the interesting thing about two equal fractions is this. Now, we've mentioned it in class before, but two fractions are equal if and only if they represent the same fraction of the whole. And an interesting consequence about this is there has to exist a number in which I can take one fraction times on top and bottom in order to get the other fraction itself. So I guess what I'm saying here is, let's look for some numbers that would relate to each other. In this case, I could relate 15 to 25. Because they're both in the denominator, I can say, what is the relationship between 15 and 25? Now, a lot of people have a natural temptation to say, well, you could add 10 on to 15, and that's 25. So let's add 10 onto the top. Unfortunately, the operations of addition and subtraction do not apply well with scaling up and down fractions. So what we need to rely upon are products and quotients. In other words, multiplication and division. Okay, so my question would be, hey, how many times bigger is 25 than 15? Now this is an interesting question because there actually does exist a number that you could take 15 times to get 25. Now it's 1.66, and I'm not going to make you do that, okay? But later in the year, I will make you find that scale factor. But I didn't expect you to know this off the top of your head. But what we want to look for is a relationship between these numbers. For example, we don't just need to look for a relationship, hey, what can I take 15 times to get 25? We can also look at it vertically. What I mean is, we could compare 3 to 15. The interesting property about fractions is, like I said, they're equal if and only if there exists a scale factor that you can multiply one times to get the other. What I notice here is that the denominator on the first fraction is 5 times bigger than the numerator. Okay? If these fractions are to be equal, then I know that this denominator must also be 5 times bigger than its numerator. Now, off the top of my head, I'm very well aware that 25 is 5 times bigger than 5. However, I do want you showing some work and having a good understanding of what it is I'm asking us to know. So in terms of showing work, you're going to get used to me writing it like this all year long. And I want you to write it like this as well. I noticed that 3 times 5 is equal to 15, and I know that if these are to be equal, then this question mark times 5 would have to be 25. So the question to ask here is, what could I take times 5 to get 25? And the answer to that question is 5. Okay? I can also check my work by putting this 5 back up here and saying, well, hey, is it reasonable? And does this make sense? There's an interesting characteristic of checking two fractions in a proportion to see if they're equal. This neat little trick is called a cross product. Now remember, product means multiply. But check this out. If two fractions are equal, you could notice that if I took, say, 3 times 25, I get 75. Now if I take 5 times 15, the interesting thing here is I also get 75. And if those two numbers are equal, then we know that these two fractions must be equal by checking with the cross product. Now, you don't have to know how to do that, but it's an extremely useful tool. Hey, this is the same problem on number 15, except for instead of comparing numbers vertically, for example, I don't know what I could take times 7 to get 8 off the top of my head. I could find it out. You give me a calculator or some long division, I can do it. But I can tell you this. What could I take 7 times to get 21? And you see what I'm doing here is I'm constantly describing the relationship between two numerators, or a numerator and its denominator. Okay, I do know this, because 8 is bigger than 7, and 8's in the denominator over here, this denominator must be bigger than its numerator also, because these two fractions are equal. The question is, what's the scale factor here? How much did we scale this fraction up by to get this one? And the answer to that is, well, what could you take times 7 to get 21? 3. So if I take 7 times 3 to get 21, I also know that this denominator must be 3 times bigger than this denominator. showing my work, once again, just writing in these arrows with my scale factor here, and these scale factors have to be the same if these two fractions are equal. I know that 8 times 3 is 24, and I do check for reasonability. Yes, this is slightly larger than this, as this one was to this one, okay? But they share the same relationship. So the question mark on this problem that I made up would be 24. But here's what I'm asking you to show. And of course, checking with the cross product, these are slightly larger numbers, but if you were to take 7 times 24, these are equal, you would get the same product as if you took 8 times 21. Okay, this is important because moving on, you get to these sets of problems. And everybody hates these. It looks like somebody sneezed on their paper on the rulers. Here's the deal. They give you 2 question marks, and the first thing I need you to notice is this. These question marks are in the same spot. So what does this tell you about these 2 measurements? They're measuring the same thing. Now, we're not going to call them the same name. Okay? In other words, we're going to use different numbers to describe each. But we really got to stop and ask ourselves, okay, remember, what is a fraction really telling us? Okay, a fraction does have 2 parts. Of course, the numerator and the denominator. I refer to these lovingly as the num and the denom. However, here's what it's really telling me. For example, on this first snot-covered ruler, we see that there are total pieces, 1, 2, 3, 4, 5, 6. We can imply that there are 6. Okay, it's kind of easier to see that. They cover this one up pretty badly down here. So we say, out of 6 pieces. Oh, my marker's running out. Out of 6 pieces. So the bottom number here tells us, out of this many total things, how far in have we gone? And the answer to that question is, well, we've gone in twice. I have 2 of these 6 pieces covered. Okay? So 2 6. Here's the cool thing about it. This fraction, whatever it is, has to be equal to this one. So what do I already know about this one? Well, I've gone in 1, 2, 3, 4 notch marks. That's how many I have. So the second equal fraction has 4 somethings. Okay? We don't know yet. We're going to find that out. But now that problem is just like these. Okay? So I say, well, how many total pieces were there? You may notice that 4 is 2 times bigger than 2. So we know that this number here must also be 2 times bigger than 6, which turns out to be 12. And just using some basic reasoning, for example, for every one of these notch marks, there were 2 of these notch marks. So how many total notch marks would be down here? Well, if for every one of these there are 2 of these, and there were 6 total of these, let's take that 6 times 2, and we get 12, which is exactly what we did here with our reasoning anyways. Okay? That should help you with those problems. Hey, moving on, looking at number 19, these are some of my favorite problems, but, you know, unfortunately, these are some of the most missed problems that students miss on tests, and the reason why is because they just kind of play around with place value. Your job here is to tell me which number is bigger, okay, honestly. But we say greater than, less than, and equal to. I think it's easy to determine here that these are not equal. If they were, they'd look alike, okay, but they don't. So which one is bigger? Here's what I'm going to ask us to do. You start in the leftmost place value, and in this case, on both numbers, we look at what happens to be the tens spot. Here's the interesting thing about it. I look at this one, and it has 2 tens. And this one has 2 tens. So I say, well, which one's bigger? And you know what? The answer to that is, well, there's a tie. In the case of a tie, you move over to the next smaller place value. In this case, we're looking at the ones, or we refer to that often as the whole number spot. Okay? They both have 3 ones, or 3 wholes. Unfortunately, we still have a tie. Moving on, over to the other side of the decimal, remember, these are not the ones. Okay, there's no such thing, but those are tenths. They both have 1/10. But once you reach this point right here, this one has 4 hundredths. This one has 9 hundredths. What usually tosses people off on this problem, throws them off, is the fact that this number was written out longer. But that doesn't necessarily mean it's bigger. Okay, this one had 9 hundredths. This one only had 4. So in this instance, this number would be bigger because, of that digit. Now, to make you more comfortable with this, if you wanted them to be the same length, a typical thing we could do is we call it annexing a 0, but we could tack on a 0 because 0 thousandths really did not change the number. Remember, 0 means not anything whatsoever. Okay? So keep that in mind as you're going through these, but just go from left to right and see which one has bigger in each place value until you've broken the tie. Now, last but not least, you're going to notice, hey, 23 is actually the same problem from your homework. That's awesome, okay? So here's what I know about it. I want you to turn a fraction into a decimal.